Hi, welcome. I'm Navneet Juneja. I lead product management for App Engine and Compute Engine. And today, we're here to talk about how at Google we're reimagining the stack for computing in the cloud. We'll spend some time talking about Google Container Engine, the new service we launched this morning that lets you run containerized applications effectively in the cloud. We'll talk about how App Engine, our platform as a service offering, is evolving. And then we'll spend some time talking about what you can expect from us in the days, weeks, and months ahead. So before I talk about the next generation compute stack, I'd like to take a step back and talk about the principles that informed our thinking around what computing in the cloud should look like. First, we believe that you shouldn't have to deal with unnecessary stuff. And by that, I mean that you should have the level of control that makes sense for your application, but you shouldn't have to deal with the things that don't add value. If you're spending your time on operational tasks that aren't critical to your application, you should be able to delegate those tasks to the cloud provider. We also believe that cliffs are for climbers. And what I mean by that is that if you're a climber, you enjoy the challenge of a new steep cliff, right? But if you're a developer, you don't want two things to happen. You don't want to have discovered many weeks down or months down the line when you built your application that something you wanted to do doesn't quite work right, and you need to throw it all out and start from scratch. Or you don't want to find that when you add the next feature in your application, everything's running well, you suddenly need to rethink how you built your application and change a whole bunch of stuff. So we don't like those developer experience cliffs. We want to make sure that the cloud doesn't exhibit those properties. And finally, we believe that one of the critical things that isn't obvious early on is that operations should be really easy. And so you should be able to design your applications in a way that optimizes for long-term operability, lower cost of maintenance, and faster iteration. And so to make that vision a reality, we really think about compute as not a set of disconnected, disjoint services that you plumb together yourself, but rather as a continuum, where you have access to different levels of abstractions and can pick the right abstraction that makes sense for your application, or even for a component of that application. And if you decide to change your mind down the line, you should be able to do so without re-architecting everything, without throwing out a bunch of code and starting again. And so concretely, what that means in the cloud platform at Google is three things. The lowest level abstraction we have is the virtual machine. This is Compute Engine, lets you run pretty much anything, gives you a very high level of control. You can run any kernel, any operating system you want, any file system you want. You can tweak kernel parameters. Whatever you need to do, you can do it right there. But let's say you don't actually care about all those physical parameters. You're running a pretty standard application. Everything just works normally without doing any crazy tweaks to the kernel. You should be able to stop thinking about that physical layer and instead focus on logical infrastructure at the cluster level, where really you tell us in a declarative way what the state you want the system to exhibit is, and then we turn around and make that state a reality. And best of all, if you are able to just focus on your application, on the code you want to write to add value for your customers, your developers, your users, you should be able to bring code to the cloud platform, benefit from a rich set of curated runtimes, a set of services that give you underlying foundational capabilities that you can use to build your application, and let us automatically manage everything that can be automated and bring your own code and run it in the platform. So let's talk about the VM abstraction, Compute Engine. It was built to offer you cost-effective access to on-demand computing. In other words, you should be able to come and spin up compute resources in the cloud when you want it, and pay for those resources only when you're actually using them. We wanted to make sure it was flexible enough to let you run pretty much anything. And we wanted to make sure that it was rock solid so that higher level abstractions could be built above it, both the abstractions that we build at Google, but also the abstractions that are emerging in the open source community, the abstractions that the ecosystem that has sprung up around cloud builds. So we wanted to make sure that the foundational building block was really solid. And to do so, we wanted to do three things. We wanted to make sure you benefited from Google's quality, the quality of service we can provide. We wanted to make sure that regardless of the size of your application, you benefit from Google's scale. And we wanted to do all this at a great price. Let's take a step deeper and talk about what that means and some of the key highlights in those three areas. First, we wanted to make sure that the underlying building block was both predictable in terms of performance and reliable, so you could really focus on building your application, not trying to keep it up and running. We also wanted to make sure that storage was available to you in a manner that was secure, so it was encrypted at rest. All our storage offerings are encrypted at rest. And similarly, our networks are encapsulated fully at the project level, so that you have access to a private network within your project, which is also global. And the benefit of that is that you can actually turn around and build an application that is global in nature, that has components that might live in multiple locations around the world. And you can wire those components together without having to do weird network tricks to get them to talk to each other in a manner that's secure. We wanted to make sure that the impact of proactive maintenance that everybody has to do, whether you're building your own private data center or whether you're using the cloud, proactive maintenance on the underlying hardware, the operating system, is critical. And we wanted to make sure that we could do that regularly to give you the best, most up-to-date infrastructure, keep it as reliable as possible, but without impacting your applications. So we built transparent maintenance into Compute Engine so that we can keep our systems running as efficiently, as smoothly as possible without subjecting you to downtime. And then we wanted to make sure that the compute and storage offerings available to you were suitable for a large variety of workloads. Whether you're running a small application or a big one, we wanted to make sure that you benefit from Google's scale. And so even though we'd regularly spin up clusters that are in excess of 1,000 nodes in minutes at Google and on Compute Engine, we also wanted to make sure that even our smallest customers who are running just 1 or 2 VMs get the benefits of that scale by benefiting from the extremely fast startup times. We wanted to make sure that the cross-sectional bandwidth, the bandwidth between different virtual machines in your project, is as high as possible, as consistent and performant as possible, because that turns out to be a key bottleneck for scaling if it doesn't work well. And we wanted to make sure that if you have an I/O-sensitive workload, let's say a database, Cassandra, or any other kind of high I/O workload, we wanted to make sure the storage offerings we gave you were not just convenient abstractions, but also gave you the high performance and the predictable speed that you expect for those kinds of applications. And then finally, we focused on making sure that all this was available at a great price. And that's not just making sure that we lead the world in terms of how we price our raw building blocks, but also in terms of how you benefit from using those resources when you need them. So for example, if you're running a short workload, and you were in the keynote this morning, you saw how much you benefit from just having to pay for the minutes you use your VMs. But if you're running a sustained workload, it turns out that actually is cheaper to run anywhere, on-premise or in the cloud, because you don't have to provision a bunch of buffer capacity to handle spikes. So if you're running on-premise, your costs on-premise are lower for sustained workloads, and for the cloud provider, it's lower for serving a sustained workload. And we wanted to make sure that you benefit from the characteristics of your workload without having to make a long-term commitment, without having to choose a specific VM size, or even commit to us. To running your workload on Google to get those benefits. So we introduced automatic discounts when you run sustained workloads. You just run your VMs, the longer they run, the lower the average price goes. And although we've launched many features in the past six months in our VM offering, I'd like to focus on 2 new things we're talking about today. The first is the availability of local solid-state drives. So in the past, we've had high performance and high throughput options, magnetic and solid-state options for our network-attached persistent disk, which is a great offering. But sometimes you just really need to take it up a notch. You need to turn to 11. And you want to have access to local flash for your application, especially if you're doing something like a very high-performance Cassandra cluster, for example. And the way that works on Cloud Platform is somewhat unique. You can take any 1+ core VM, so any standard VM, any high memory VM, any high CPU VM, and you can attach flash to that. And you can do that in blocks of 1 to 4 375 gigabyte chunks. And in doing so, you can get up to 680,000 read I/O. And this is 4K random reads. Better yet, as you might know, flash devices need proactive maintenance as well, especially because of the way those devices are built. And often when you decide to use flash for your workload, you have to deal with thinking about, how do I maintain that device so it keeps running effectively? We built transparent maintenance to take care of that problem for you as well. So we extended our transparent maintenance technology that works in the data center for your VMs and said, if your flash device needs to be maintained, we'll transparently migrate not just your VM, but also your storage, and your application will keep running, and we keep the infrastructure working really well. It's available at a great price, less than 22 cents per gigabyte per month. And like all our other storage offerings, it's encrypted at rest. We're also talking about Compute Engine Autoscaler this morning. This is built on the same auto-scaling technology that we at Google use to scale our own applications, so it's been proven. And it has a very simple and powerful abstraction. All you have to do is choose a metric that you want to scale your fleet based on. Let's say that's the CPU use of your fleet. You tell us what target you want to hit for that. Let's say that's 80%. And then you walk away, and our systems will take care of spinning up VMs when your CPU utilization goes up, or we'll take care of spinning down a few if your CPU utilization drops. So we keep your CPU utilization within those bounds. We support a bunch of different metrics. You can also scale based on custom metrics in cloud monitoring, on the utilization of your HTTP load balancer. Best of all, you don't need to pre-warm your application to get the benefits of auto-scaling. Once you've set those targets and told us what you want to do, it just works. And now to demonstrate that, Prapi.
So hello, everyone. We'll see how to use the autoscaler that Navneet just introduced on a real-world application, the Go playground. Some of you may be already familiar with it. It's a very straightforward application. You enter some Go code. I can say hello GCP live. I click run, and my code gets compiled and executed somewhere in Google infrastructure. So we'll see how to take this application and run it on Google Cloud Platform using the autoscaler that Navneet just introduced. So for that, I will run the command, OK, Google, create an autoscaled group of Compute Engine VM running the Go playground. It's not implemented yet, but I'm sure someone is working on it somewhere. So let's see how we can do the same thing today using gcloud. So the first thing I need to do is to tell Compute Engine what I want to scale. So for that, I will create a new instance template. I will give it a name. I will point to an image that is a container VM optimized image. It's a VM image that we distribute that is optimized for container workload. And the last thing I need to do is to point to a manifest. This manifest will define the containers that I want to start with the VM. So I have to wait for the template to be created. Here it is. And next, I need a group of VMs that I need to create a group for my VM to scale. So for that, I will use an instance group, a command group. I will define the zone into which I want to run my VM. Here, I want to run them in US Central 1F. I will give a name to the group, and I will point to the template that I just created, effectively telling to Compute Engine to always create VM based on these templates. And the last thing I need to do is to define an initial size for my group. Here, I want 10 VM. So here, it's creating my group in the background. So now that I have my instance group, I could stop there, and Compute Engine will happily manage this instance group for me and make sure there is always 10 running at any point of time. If one goes down, it will restart a new one according to the templates. And the next thing I want to define is I want to scale those VM. So I want to create an autoscaler object, and I want to tell Compute Engine how I want to scale. So the autoscaler will live in the same zone as my instance group. I will give it a name. I will target the same group that I've created before. I will give it a maximum number of instances that I want to create. Here, I want to scale up to 200 VM. And I will also define a minimum of instances I want to keep. Here, when scaling down, I always want 10 VM. And the last thing is I need to define the policy that the autoscaler will use in order to decide if it needs to spin up new VM or spin down some. Here, I'm going to scale based on CPU utilization. Meaning here, I set the target CPU utilization to 0.5, which means that across my fleet, when I reach more than 50% utilization, the autoscaler will use that as a signal to create new VM. And across my fleet, when I'm below this utilization, the autoscaler will use that as a signal to scale down. So let's see. Let's stamp the demo gun again and see if our instances are running yet. Yes, that's good. And let's check if the application is serving. It's ready. So let's take a look at this IP. And here we see the Go playground, the same application that I introduced before that is running on one of these auto-scaled VM. When I click run, it will contact the backend and compile and run my Go code. So when Navnev enters stage, I actually set up a load test across an autoscaler using a similar setup. And we'll see how the load test went like in the 10 minutes that came from Navnev entering stage to what we are now. So here we can see that in 10 minutes, we went from just a few thousand QPS to more than 1.5 million QPS. And we went from our tiny group of 10 instances to more than 200 instance running. So this is like to show how to use the autoscaler in action. And with that, we'll go back to Navnev.
Thank you, Prapi. So to recap, you told us what you want to scale. You told us how you want to maintain the right utilization. And then we went from 0 to 1.5 million QPS in 10 minutes.
Yeah, that's pretty much it. You forgot about the part where the demo didn't quite work well.
That's true, too. Yes, we also
I think, like the
sacrificed him to the demo gods, and then, yeah.
The 1 million QPS pretty much like erased everything. So.
Thank you, Prapi. So enough about the VM abstraction. Let's take it a level up and think about logical clusters. And for that, I'd like to introduce Eric Hahn, Product Manager for Google Container Engine.
Thank you, Navneet. Hi, I'm Eric, and thank you for joining us. The start of a new product line is an important moment, and we at Google think that clusters are going to be an important way for how users compute going forward. Clusters represent a fundamentally different abstraction for applications and operations and provides a much richer, better set of tools. And from a business person's point of view, clusters allow your teams to be much more productive within the existing set of resources they have. And with the announcement today, we've embraced clustering for a multi-cloud world. So let's go through how. First, we're going to talk about containers and how containers are changing the world. And second, we'll go into Kubernetes and Google Container Engine and talk about why it's the best way to run your Linux application containers. As we talk to customers around the world, containers are absolutely changing their lives. It's making it much easier to develop, build, and run their applications. And Docker has done a fantastic job at this. They've made it very simple to build a container, make it portable, and customers are picking that up, as is the industry. Containers are a much better abstraction, and they're targeted at the right layer. So to talk about how, let's take a step backwards. This is a virtual machine, obviously. And with vanilla virtual machines, I have an idealized piece of hardware. Here, I'm able to have full access from the guest kernel on upwards. I have my library and my applications. It gives me full control. At the same time, it has its downsides. It's not portable. That idealized piece of hardware is tied to the VM image itself. It's opaque, and customers cannot bring that and move it across clouds and across providers. And so we see customers running into this problem. They want to get more utilization out of their resources. They side-by-side deploy apps that they own, and the libraries are conflicting. And from that perspective, they start to go down a few roads. One is they might restrict the app development cycle. They might restrict the libraries, and that impedes the ability to make richer applications. And the other one is they add integration cycles so that application developers get pulled into host integration problems, and that does not improve the ops lifecycle either. And some approaches we've seen with customers is they give every application version its own virtual machine. So here, I absolutely have isolation. Each application is put into this idealized piece of hardware. They have a VM to itself. And of course, the libraries are not conflicting. That's OK. But the redundancy here will cost me. I have this guest layer that's spanning in each VM. It's more to maintain. And more importantly, that kernel has a different velocity than the application on top. I want to be able to control and articulate each independently. I don't want to manage my apps like I manage my kernels. The next challenge is it creates problems for planning for peak utilization. Customers are over-provisioning, and that further slows down the procurement cycle and their app development cycle. And so we get to containers. Containers create the right abstraction at the right layer. Docker has done a great job at this. Your app is special from the perspective of the library and the app code on top. We're taking an idealized piece of hardware, and we're lifting up and instead creating an idealized operating system. It's portable. It spins up on the order of process, and you're not locked in. So we can compose those, and we can take many application containers and side by side put them onto a node. Each container and each application in a container has its isolation from the library's perspective. At the same time, we're able to preserve the same portability aspects. So this is a big improvement from what we had before. But we're still talking about the individual node level. Google could not operate if it programmed at individual nodes. Gmail, Search, they're all looking at a higher level construct. And so that higher level construct that we really need as part of our solution is a cluster. A cluster is simply a collection of nodes and a set of tools to help you manage that way. So we talked about containers, we talked about clusters. Now let's talk about, we talked about containers, we introduced clusters. Let's talk about Google Container Engine. And given that it's a start of a new product, it's important for us to go back and we can look at three influences in how we built the product. The first is Google itself. We have over a decade of cluster computing experience within Google. It's informed and been a key part of the lessons in how we built Container Engine. The second is we've been talking to customers. They've provided us key inputs as we built out our product. And the third is Kubernetes itself. Kubernetes is the open source project started by Google. It's a cluster compute with full implementation out in the open. And it's been a key influence on Container Engine. So at Google, we launch over 2 billion containers every week. And from that, we find that we could not operate in this level if we focused at the node level. We have to be thinking at the cluster level. So some of the important lessons from clustering within Google is that you want to let your users, in this case, developers of Gmail and Search, you want them to operate and tell you what they want to achieve. You want them to specify the intent. Your system should provide the constructs to implement the how, and you don't want to mire the two. The next important point is you want to make it resilient from day one. You want the cluster to help you with your resiliency. You don't want to be backporting in resilient patterns. And the last is that you want to keep the system and the architecture pluggable. Within Google, we have many layered systems and many separate systems, and users can compose actions based on using those different systems. And at the same time, those systems can have components swapped out and plugged in so we can be evolvable over time. For Container Engine, the next key input has been talking to our users. In talking to our users, we see that they're trying to deploy 10, hundreds, and thousands of containers. And even though we're talking at Google about deploying 2 billion containers every week, those lessons also apply here. We see that customers are struggling, though. They're struggling with host-based tools and patterns that are taking away from the original promise of portability. It's locking them into a set of patterns that are rigid now and won't let them scale. So we want to address those. At the same time, we also see that when we talk to our large customers, they are already telling us they're running in a multi-cloud world. For them, they need their tools to also support multiple clouds. And the third input into Container Engine has been Kubernetes. If you don't know, Kubernetes is Google's invitation to build cluster computing in the open. Here, it started in June, and it's since grown and it's been very successful. Some of the key lessons we've had from Kubernetes have been, we start in the open. All our design discussions start very detailed. We evolve from the goal level up, and we work with the community as we design out the patterns. And we know that Kubernetes will work across multiple clouds. Our partners, our community, they've helped us shape the APIs, and they've implemented it to their cloud providers as well. So we know that Kubernetes will work if you take it and install it on any cloud provider of choice. And from that perspective, there's a third important lesson. It's the same as we had within Google, which is keep the system and the architecture pluggable. And from that, customers and partners can tune it and take the default implementation and evolve it as they need. So let's take a quick moment to take stock on Kubernetes. Kubernetes started in June, and in the 5 months, it's since grown. It started with a contribution from Google. It now has over 100 contributors, as well as over 4,000 GitHub stars. It has 9 partners, all from the top tier, that are extending and making Kubernetes work on their clouds, and we're adding more. At the same time, we've been hard at work implementing more features. We just recently released 0.4.2, and we added richer scheduling, integrations with open source logging tools, as well as improvements in our DNS integration. So what is Kubernetes? Kubernetes is a technology that's done great, but let's briefly dive into some of the concepts that are important for cluster computing. The first key concept is a pod. This pattern of co-locating two pieces of code is prevalent everywhere. An example could be I have a content management system. It's providing static content for my Nginx web server. You always want these to be scheduled together. A pod gives you a simple ability to do so. Importantly, a pod does not interfere with your app development cycle. Your developers are producing containers, and the ops users are creating these pods that wrap them. Once I have a pod, I'm able to declare and define how to create the pod within a manifest. And that gives me this repeatability. I can create a pod, and if the physical machine underneath it dies, I know how to recreate the identical pod. Pods also serve as a place where we can assign something called labels. So labels is a lesson that we've learned through many bruised knuckles within Google. Before we had labels, or before the idea of labels, one thing people started to do was they started to build higher-level systems and dashboards by looking at how deployments were occurring. And they were smart, and they were able to reconstruct and to identify what might be their front end or their different serving systems. But if you let your users get mired into the details, it creates a brittle architecture that doesn't let them grow and also impedes as you evolve your system. So labels solve this problem. It gives you a piece of metadata. It's specific to your need. And in this example, I can have a system on the right-hand side who all they want to know is all the V2 error systems. It's completely independent. They can assign labels to the pods, and the pods themselves can be queried for V2 systems. And on the other side, I can have all the front ends. So these are constructs that I can build over each other. And labels also serve as something which I'll call a membership identifier. You can use a label to trigger higher-level systems, and the example would be replication controllers. Replication controllers in a Kubernetes world is just one kind of controller. I can have other kinds, like a job controller that runs things to completion. But a replication controller's main function is to ensure that pods stay up at the desired state. And for a replication controller's desired state, that's the number of pods that I want running. The other part with replication controllers is I can compose and trigger actions. In this example, I can have on the right-hand side a V2 system that I want to canary test. I can use the replication controller to specify the desired state, and I have fine control over adding each pod as it goes out. And if any of the system dies, if the hardware fails, a replication controller will ensure that the number of pods are up and running based on the desired state. The next higher-level system, and the last I'll discuss, is services. So if we take a step back for a moment and stop thinking about clusters, and we think about a container and a single node. I have a container. How do I find it? How do I discover it? And that's the problem that services solves. I can create a service. It serves as a stable endpoint for my clients to bind to. If the pods in the implementation that the service routes to die, the front-end client, or the client of the front-end service does not need to rebind. So services provide this stable endpoint, and it allows us to create these richer microservices that your ops personnel can create, and it does not infer opinions onto the development cycle. So let me give an example. Here I have a services front end, and I have two separate replication controllers. If I want to take the front end, if I want to take one of the pods offline, I can take it away from the service, and then I can access that pod. I can SSH into the containers itself, debug, look at the logs. I have that fine-grained control of my system. My service stays live. The browsers are still hitting that service in this example, and the service will route to the pods that exist. And with the other replication controller, I can scale out. It's important here that the replication controller and the services are decoupled systems, and you have that fine-grained control. So Kubernetes, we feel, is the best way for you to build your cluster computing infrastructure. So let's say you don't want to build it. For many of our users, they do want access to the implementation, but for some of our customers, they want a product or service that does that for them. This is why we built Google Container Engine. Google Container Engine takes inspiration from a decade of cluster computing within Google. It's inspired by our open source community, and it reimagines the cluster computing experience for our users. And it puts the power in their hands so you have a cluster at your fingertips. And with our support for Kubernetes, you have support for a multi-cloud world as well. let's pull it all together. I have a Google Container Engine system. On one side, I have a single set of API and tools. Through those single set of API and tools, I can manage my cluster and that Kubernetes workload. With Kubernetes, I have the open source community. I have Docker support. I also have the ability to orchestrate containers. It's portable, and I preserve that. With Container Engine, I'm able to spin up a cluster in seconds. It manages the Kubernetes workload for me, and it provisions the underlying system. Now let's give a demo to pull that all together. And for that demo, let's rejoin Proppy. So we want to show a cluster and the workload. We want to show that the customers can bring their containers without modification. And from that perspective, once I have the containers themselves, I can create these constructs like services, et cetera, and it gives me full control. It starts with a node, but I don't have to actually manage the node myself. I have a cluster to do that. The cluster will create the nodes. So to see that, let's show how we would create a cluster.
So I use the same command again. OK, Google, create a new container engine cluster. I already have one. It's called GCP Live. So let's see how I really created it. So I'm using a new command group that is called container. I'm using the cluster subcommand. I want to create my cluster in US Central 1B. I give it a name and a number of nodes. Here I want 3 nodes. And here you go. You have your cluster, Eric.
Great. And let's just take a brief step back and peek behind the covers and see how these nodes are implemented.
For that, I can try to list. I can list like the instances that are running in the same zone as the cluster, the same compute engine instances. I see that I have 4 instances. The first one is the master. It's holding like the API server that we make that our command line tool will talk to. The 3 other VM are running nodes. Those nodes are going to be that's the nodes that are going to get used for running the actual container workload.
Great. And the K8s there is just a moniker for Kubernetes. It's saying that we're using Kubernetes to create the cluster, and these are the same rock-solid VMs that Navneet talked about. So that's great. I have a cluster. It has nodes. It has a master to orchestrate all that. And from here on out, I'm going to think at the app or the cluster level. And from the app perspective, let's take a look at the application itself.
So here I'm going to one of the nodes on port 1990, and I can see that I have the same Go playground that I ran in the previous demo, the exact same Docker container that are running on Google Container Engine. If I click Run, my front end will talk to my backend and compile and run the Go code that I specified here.
Great. And so here the client that we're illustrating is a browser. The browser is connecting into this front-end tier. The front-end tier is connecting into a back-end tier. And we're using the cluster construct of a service to encapsulate that front-end service, the front-end tier, as well as the back-end. And so from a client or the browser's perspective, it just needs to know the front-end service address. So let's take a look at those services.
So I'm going to list the services by using the services subcommand now. So I give the name of the cluster, my zone, and I list them. So here I can see that I have 3 services. The first is the front-end services. There is a selector associated to it and a port. The port is 9090. It's the port that I hit in my browser before. And what the selector means is that every time my browser hits this endpoint, it will try to find a pod that matches this label. So it will dispatch and load balance the request across any pods that match the query role frontend. And similarly, I have a service for my backend. So you remember when I hit this run button in the application, I want to send this like Go code to some of the backend to compile and run it. And what the front-end pod will actually do is contact the backend service on port 8080, and similarly, the request will get load balance across any pods that match the query role backend.
Great. And so with these services, I have the ability to independently manage each application. All right? And the application itself is implemented into pods, but the caller does not need to know that. The caller just knows to bind to the service. And so Proppy and I, are managing the front end in this example. So let's take a look at the pods that implement the front end.
So for that, I will list the pod. So I can see that I have 3 pods running. The pod for the front end You can see here that I have the same collection of labels I was talking about. The frontend are tagged with role frontend. And I have the backend pod. And it's tagged with the label role backend. I can see the nodes where they are running, and I can also see the container image they are running too. Here you see that I'm using the same container image I was using in the previous demo.
Great. And so we only have one instance of the front-end pod. Let's say that we've been wildly successful from the earlier demo, and Go Playground's getting tons of traffic. I want to scale out the number of front-end pods, but I want to do it at a desired state. As an ops user, I don't want to have to imperatively recreate each pod. We have cluster tools to do so. So with that, we would use a replication controller. Propi, can you show us a replication controller?
Yeah, I'm going to take a look at the manifest for the replication controller. So here, the first thing of HDRest is the pod template. It's what defines the workload that we want to run. So we have a simple YAML manifest that is composed of two containers. The first container is a Go application. It's my front end. It's a dynamic part of my app that will display the UI and under the request. Here, it's an image that is called Go Play. And the thing that is interesting is that I have another container in the same pod, an Nginx container. And this container is used to serve static file. And since these two containers are co-located inside the same pod, it's trivial for the Nginx pod to offload dynamic requests to the Go app. And the pod itself behaves like a single entity and gets scheduled by Kubernetes and always move from node to node together. This last container, the Nginx container, is exposing a port. It's exposing port 80, and the name of the port is web server. This is a port that gets referenced inside the service definitions that I've shown earlier. Something also interesting is the labels that we set on this pod. Every time the replication controller creates a new pod, it will associate role frontend to this, the label to this pod. So our replication controller needs two parameters in order to scale our pod. It needs a number of replicas that we want to keep in the system. Here we want 5. And it needs a replica selector, which is a query that it will run across the cluster to know if there is too many pods or not enough. So at any point of time, my replication controller will query the cluster with this role frontend replica selector. If there is, say, 4 pods running, it will start a new one. If there is 6 pods running, it will kill one. And so I can use this configuration now and scale my front-end pod for 1 to 5. So for that, I'm going to use the container command with the replication controller command group. And I'm going to point to the manifest I've just shown. And here you have, I scaled your front-end, Eric.
Great, but what about the pods?
Okay, I will actually show you that it's true. So let's list the pod again. And here you can see that I have 4 more pods running. What's interesting is that the replication controller only created 4 because we already had 1 pod in the system matching this replica selector. So it already needed to create 4 to match the desired state that we expressed in our manifest.
Great, so you were able to take use a replication controller to scale out your front-end instances. Let's take it back to the application. What does it look like?
So here, I have the same application. I can refresh my browser. And you see that it's still serving. It's still working. And in the middle, we change the number of pods that are running. What is actually happening when I hit my browser is that I hit the service endpoint. And the service endpoint here will find any pod, including the new one I created to serve this request. And similarly, when I click run, the Go code will get sent to the backend service endpoint. And the new front-end pods that I created, they don't have to learn about where the backend is. They don't have to discover them. They already know about the backend service endpoint. So all they need to do is to contact that endpoint, and the request will get dispatched to one of the backend pods that match the label selector query on the service. And that's it.
Thanks, Propi. So the important part for me as an ops user is that we were able to take a live service. It was resilient. We were able to have one of the pods be touched, attenuated, and we can use a replication controller or the cluster concepts to help me manage my desired state. And for the developers, they did not have to change their code. They did not have to be mired in the details of how I built that resilient microservice. So to recap, we have a new service, Google Container Engine. It gives you a cluster within seconds, and it lets you have fine-grained control over desired state. It's designed for a multi-cloud world with support for Kubernetes. And on behalf of the Google team, it's my pleasure to share that we are open alpha today, Please go use it and share with us your feedback. And we're working hard with updates on pricing and SLAs. With that, please let me welcome our next speaker. Astrid Atkinson is an engineering manager at Google's App Engine product, and she's here to share with us more about App Engine. Thank you.
Hi, everyone. So as Eric said, my name's Astrid, and I'm an engineering manager here at Google. So Container Engine is really great technology for when you want to exercise super fine-grained control over how your production services are configured and deployed across your compute resources. But let's take a step back and talk for a minute about managing systems instead of take a step back. Instead of talking about managing systems, let's talk about managing applications. So as a developer in the cloud, there's a lot of stuff that you have to take care of. Stuff like getting your code onto multiple machines, managing production configuration, resource provisioning, and so forth, which might really not be how you want to spend all of your time. A lot of this stuff is really just overhead. It's the same every time you have to do it. It's similar for most applications, and it's similar for most users. And so at a certain point, it might be nice just to kind of let the machines take care of it for you. And so that's what App Engine was really built for. And I'm going to talk a little bit about what we're doing with App Engine and how we're working to evolve the platform. So a typical serving stack kind of starts here. If you're developing a new application, you're going to start with a single node. And there'll be the stuff that you really care about, which is your app code, your libraries, and so forth. There'll be the application environment. Then there's the guest kernel, the OS, the hypervisor, all the stuff associated with the VM. And within the app environment, there's also a few elements that are pretty generic, right? You're pretty much always going to have a web server. You're pretty much always going to have an app server. It's usually going to be a language runtime interpreter, and so forth. And so App Engine was really built originally to abstract these components, right? They provide these as kind of general purpose platform. So let's say that here's where you start with a single node. But as you're moving from dev to prod, that's probably not where you end, right? You're probably going to want a whole bunch of nodes. And then you're going to need a load balancer to accept traffic for those and send traffic across all of them. And then since you're running in the cloud, you're probably also going to want an autoscaler to size the pool up as you're getting more traffic, and then size it back down when you're not using those resources so you don't have to pay for them. And something that we've also observed is that typically over time, as applications mature, the developer will want to divide the system up into areas of specific functionality. So we showed in the earlier example, a kind of a trivial example. It has a front end and a back end. But usually this gets pretty complex pretty quickly in production. A lot of times there'll be batch processing, feed aggregation, upload processing, billing, interacting with third-party APIs, those kinds of things. It gets kind of a lot more complex over time as your app grows. And then each of these also needs its own load balancer, its own autoscaler, so that you can tune them individually. It's kind of a lot. And then you probably also want a high availability configuration, be deployed in more than one zone. And then depending on your app profile, you might want to be in more than one region, right? You might want to get next to your users for latency reasons. And if you're a global company, you may also want to do this globally. So this gets complex pretty quickly. And that's before you even consider things like updates, rollouts, rollbacks, and so forth. All of the stuff about managing your application over time. So one of the things that we've observed at Google is that while large services can afford the overhead of dedicating ops, SRE, DevOps stuff to managing all of this production infrastructure, for a lot of services, having to manage all of this really creates drag in terms of the amount of innovation that a team can generate. Right? If the developers on a team are spending all of their time working on running stuff in production, that's time they're not spending building stuff for users. And so something that we noticed at Google as we tried to abstract these common layers so that people didn't have to worry about it so much is that it really tended to increase the rate of innovation on the team as developers were able just to focus on building awesome applications for users. And App Engine was originally the externalization of this philosophy, right? The idea that we could take and abstract all of the common elements of running a system so that developers could really just focus on their code, and Google could kind of take care of the rest and provide a suite of tools for managing that application over time. So over the past year, we've been working really hard on evolving this, so particularly focusing on openness and flexibility. Back in Cloud Live in March, we announced Managed VMs, which is App Engine environment, App Engine management infrastructure with virtual machines. So with the new App Engine environment, you get the same high productivity. You can focus on your code, and Google can handle all the plumbing, the scaling, the load balancing, provisioning, and all of that stuff. But you can now do it with any Compute Engine VM, which means that you can access different RAM and CPU footprints, and you can also access all of the tools associated with the underlying GCE layer. That's kind of cool. It's also more flexible because you can choose all of the libraries and dependencies that your app needs. And if the App Engine runtime doesn't work for you, you don't need to use it at all, right? You can just bring a container that has your own runtime in it, and the management infrastructure can take care of that for you. Since the initial launch, we've been super hard at work adding features and also working on reliability. So a couple of things we've added are integration with some of the cloud platform tools, load balancing integration with GCLB, cloud autoscaler integration with the cloud SDK, so that it's really easy just from a tooling perspective to drop down to the underlying infrastructure when you need to. And then we also added Docker support so that you can take advantage of the portability and the flexibility that the containerized environment provides. And best of all, I'm super happy to announce that as of today, we're opening this up to public beta. So you can take advantage of this with your own workloads right now, and let us know if you like it. Oh, all right. So with that, we're going to hand back over to Prapi for one last demo.
OK, so as Astrid mentioned, there is sometimes, like when you are a developer, when you don't really want to worry about VM, you don't even want to worry about clustering or container. You only want to focus on your app. And for that, we can use the same command again. I hope the joke will not get too old. OK, Google, take care of my app. Use App Engine. And so that's what I'm going to do. I'm going to run the same demo that we've deployed before on Compute Engine that we orchestrated on Kubernetes and like running on my laptop using Google App Engine SDK. So let's take a peek at the backend. We focused a lot on the front end during the Kubernetes demo. Now I want to talk more about the backend. So my backend is a piece of Go code. I have a Docker file for it in order to build a container. It will build the same container that I used for the previous demo, thanks to Docker portability. And the only thing I had to do in order to transform this Docker container into an App Engine app is to add an app.yml file. So let's take a look at what the app.yml file looks like. So some of you may be already familiar with the App Engine configuration. We define a module name. Here our module is backend. We define a version. But here there is two new flags that I would like to introduce you. There is a VM true flag. It tells that we want to run on managed VM. And there is a runtime custom flag. Even if we are using a Go app here, it's not like your random friends Go app. It's actually compiling Go code. It's running in a sandbox. It's pretty custom. So for that, we need to bring our own runtime. We need to bring our own Docker container. And that's what the runtime custom stanza is saying. It's saying, like, using the Docker file that I have in the same directory, took my app code and build a container for it. So let's see how we can use the Cloud SDK to run both the front end and the back end on my laptop. So here it will build the container for my front end and my back end, and the front end will start serving on port 8080. So I can go to localhost, and here I have like the same application that I have before with my two components, my two modules. And when I click run, the front end talks to the backend module, compile my Go code, run it, and return its output. So I think like the app is ready now. I've tested it. It's working locally, and I want to deploy it in production. So for that, I use the gcloud preview app command, but with the deploy keyword. And here, I'm deploying a new version of my app in production. So same, it will compile my container if they are not already there and start provisioning my VM with the containers that are running in them. So I already did a deploy of a version before this event. And here we can see it's running on my own app ID, on my own host name. I can click run. And similarly, the front end is talking to the backend, compiling my Go code and running it. And it will just want to like pause a little bit and think about like all the things that were automatically done for you. We didn't have to worry about provisioning the VM with our container. Like the deploying system automatically copied our container into the cloud storage and provisioned the VM so that I can fetch this container and run it. We don't really have to worry about creating a load balancer or a DNS entry or even an autoscaler for our app. Like when we are hitting this host name, it automatically gets load balance and autoscale across one of our modules. if we are getting more traffic, for example, when Go 1.4 launch in the following weeks or maybe months, I don't know, like the infrastructure, when people will rush to the Go playground in order to try the new Go 1.4 feature, the app will be available and be able to handle the traffic spike. And also, we didn't have to worry about like copying static file or provisioning front end and making sure they get cached. All our static file gets uploaded to Google rock solid front end and get cached automatically. So I want to take a peek under the cover and see what our app is looking inside the console. So here, when I go in the App Engine section of the console, I have like I have an overview that gives you like some health metric for my app. I can see the latency. I can see the more popular endpoint for my app. And if I want, I can dive into the version I deployed. Here I can see that I have two versions, version 1 and version 2. And with one click, I can enable traffic splitting and say route like, say, 10% of my traffic to version 2. And so I get to be able to test change with real users without compromising my live services. I can also take a look at what instances are running. So here for my front end, I didn't actually get any traffic, but I could take run here, reload, an instance should start, or I could even take a look at my backend. I can see that I have two backends running that are handling requests. I can see some app level metric, like loading latency, or even latency for requests. And I can also look at the logs of each module. So here I can take a look at the logs for my backend, for example, and see that it handled a bunch of compile requests. But sometimes you need to go deeper. Like I said that you don't want to really think about VM, you don't really think about clustering, but sometimes you need to. You need to take a look at this VM that is running your app. And for that, you just need to go to the instance section, and when you click here, you actually go to the compute engine section of the console. And here you can see more machine type level metrics like CPU utilization or network traffic or disk traffic. You can also see how the underlying, it's fully transparent because you see how the underlying like VM gets provisioned, which parameter it gets used, which copy it has, and which API call it's able to make. And you can even SSH to it if you need to troubleshoot, and you can like list the container using the standard Docker tool. So with that, I will go back to Astrid, and thanks for watching the demo.
All right. Thanks so much, Prapi. Actually, can you guys take it back one slide? Thank you. So to recap, we just showed a couple of things. One is that portability is really key to the compute continuum, right? Prapi was able to take the same container that we used in the raw VM and the autoscaling demo to start with, run that in Container Engine, and then also run that in App Engine without any modifications. Another is that it's pretty easy to move back and forth. He showed you a little bit of the configuration. It's really just as simple as making a config change. And the last is that all of the additional application support stuff that comes along with App Engine can really make it a lot easier to maintain your app without having to worry about setting all of that up for yourself. So this is functionality that really aligns with a few core principles, just kind of getting back to this, which guide our thinking about what makes a great cloud platform. So first is developer efficiency. And we think it should be really easy to get started. It should be pretty straightforward. It should be zero friction. You know, things that should work well together. And when you're ready to move from local development to production, it should be just a click. Likewise, when you want to move from your test instances to your production instances, that should also be really straightforward. But we wouldn't really be doing you any favors if the whole system fell over just at the point where you started to reach real success, right? Like, as your app scales up, the infrastructure needs to scale with you. And so by building on Google infrastructure, we're able to guarantee that we'll be able to scale with you, whether you have 100 users or 100 million or a billion, hopefully. Let us know if you have a billion. And also, by building on top of the underlying generally available compute engine and cloud platform elements, all the power and flexibility of the infrastructure as a service platform is available to you as well, without having to punch out of the App Engine environment. And lastly, we're doing this in the open. We're starting to build our runtimes on GitHub, where you can fork them, customize them, or even replace them if you want to. Now, as we showed earlier with Container Engine, we're building on top of open source systems to build the functionality that we're rolling out today. And the ecosystem is growing at a phenomenal pace right now, right? Like those open source systems are really leading the way. And here at Google, we believe that the future of the cloud platform is genuinely wide open. So with that, I'll hand back to Nav, who's going to talk a little bit about the road ahead. Thank you.
Thanks, Astrid. So what have we learned and where are we going? Well, first, we really believe that you need to think about operations from the get-go. It really is all about operations if you're building a successful application. And so we want to make sure that those early design decisions that drive your long-term costs and make your applications either maintainable or not are as easy as possible to make. We want to make sure you have the right building blocks so you can factor your application in a way that makes sense. And then we want to help all of our developers fundamentally fall into the pit of operational success. In other words, we want to make it as easy as possible for you to get started right so that things just work well from there on. Kubernetes is the first project in cloud that we've done in the open source community, and we've learned a lot from it. The community has really helped us shape the API. It's helped us build a better product, unlocked the ecosystem with the broad list of partners that Eric talked about. It's let us iterate very quickly and in the open, and we look forward to trying that model with other projects in the future. And then finally, you should start thinking about compute not as a set of different services, but as a continuum of abstractions, where you can pick and choose the right abstractions for your applications or components and change your mind without incurring a significant penalty. So you can move up and down the abstraction stack and focus on building your application and let us do the rest for you. Thank you.